In this video, we provide an introduction to nuclear chemistry. Generally, when we study chemistry, we study transfer reactivity and properties of atoms and molecules based on the electronic structure of those atoms and molecules. Now, nuclear chemistry worries about other aspects of the atom. In this case, it's the nucleus that we're going to be concentrating our efforts on. All right, so again, remember what an atom is. We have here a nucleus, and then has positive charge, and then the mass, and then in the periphery we have electrons. And again, usually in chemistry we worry about the electrons, but there are aspects about the nucleus that are also interesting. Right, so just to remember how we dealt with atoms, remember that an atom is determined by its atomic symbol, but we also have to specify the number of protons, the atomic number, and then the mass number. Okay, so that Z, that is what we called the atomic number. And then A is the mass number. Okay, so there's going to be three main players, three main particles that we're going to be talking about. Okay, you actually have the number of protons, okay, and that is going to have an atomic number of 1 and a mass number of 1. That's a proton. And neutrons have an atomic number of 0 and a mass number of 1. And then the electron, which does not have any contribution to the mass number, and has an atomic number of -1. Okay, so obviously when we think about these atomic numbers and mass numbers, okay, the atomic number is simply going to be the number of protons that you have in the nucleus. Okay? The mass number is going to be equal to the sum of the number of protons and the number of neutrons. Okay? And that specifies completely a particular isotope of an atom that we might be interested in. Well, so it turns out that there's about 2,000 or so known nuclei, even though we only have about 118 or so elements in the periodic table. Okay, so that tells you that you have many isotopes for many of those elements that you have in the periodic table. So it turns out that of the 2,000 known nuclei, only about 279 or so are stable with regards to the composition into other isotopes. Okay, so when we actually look at what controls the stability of those 2,000 nuclei or so, okay, we can try to plot here how things change as a function of the atomic number, okay, by controlling what is the ratio of the number of neutrons over the number of protons. Okay? And then what we find is that if you take this to be 1, okay, so that is the atomic number or the number of protons, okay, that will be a 1-to-1 ratio between neutrons and protons. What we find is that when the atomic number is low, okay, so 20 protons or so, what we find is that most of the stable nuclei have a ratio of neutrons to protons of about 1. Okay, so when you find the stable nuclei, they are actually going to be around that line. Okay, however, once you start to increase the atomic number, once you go through nuclei that have a number of protons over 20 or so, what you start to find is that the stable nuclei tend to have ratios of neutrons to protons a little bit larger than 1. Okay? And all these dies off at about 84, okay, which is going to be right here. Okay, so once you get to atom with number of protons 84, that is polonium, no elements, or no isotopes of the elements that have an atomic number of 84 or above are actually stable. Okay, so stability finishes at about 84 or so. Okay, so again, these are where the 279 stable nuclei are distributed more or less, and the rest of nuclei that are known are going to be either above or below these stable nuclei. Okay, so when you actually then take a look at what controls the stability, we can say that for low number of protons, low atomic number nuclei, okay, a ratio of 1-to-1 of protons to neutrons, that seems to be quite seems to confer some stability. And then when you go to higher atomic numbers, is an excess of neutrons over protons that provides stability. Within that, what we actually know is from experimentation, by just looking at what atoms are stable, what we know is that typically combinations of even number of protons and even number of neutrons, those seems to provide the larger number of stable isotopes. Okay, so again, when you have a number of protons that is even and a number of neutrons that is even, again, that seems to be particularly stable. So we can write here elements such as, or isotopes such as oxygen 16-8. Okay, so here you will have 8 protons and 8 neutrons. So that's the ratio of 1 to 1, and you're in the low mass number or number of protons type of range. Okay, that is very stable. And then we have carbon, okay, also 6-12. Okay, so 6 protons, 6 neutrons, even a ratio of 1 between them. Okay, that is also in this range right here, and that is also quite a stable nucleus. Okay, and then if you actually have an odd number of protons and number of neutrons, then those tend to be more unstable. It doesn't mean that you can't find any nucleus with an odd number of neutrons and protons. Okay, what happens is that that is more rare. Okay, this is far more common. Now, in addition to this, there seems to be some magic numbers in the number of protons or neutrons where we find very many stable isotopes. And those magic numbers tend to be 2, 8, 20, 28, 50, and so. All right. So when you have that either the number of protons or the number of neutrons has these magic numbers, then we find that those isotopes seem to be rather stable. Okay. So in this video we have introduced the concept of nuclear chemistry, and then we have examined empirically what are the characteristics that provide stability to a nucleus. In the next video, we're going to talk about when you have an unstable nucleus, what are the pathways whereby that nucleus decays into other nuclei.